Welcome everyone to the week 4 of our project management course. Today we are going to dive into one of the most widely used project scheduling technique. It's called the program evaluation and review technique, or simply called PERT. This technique is essential for managing projects where there is uncertainty in your activities durations. By the end of this session, you'll understand what PERT is, how it differs from the critical path method, and how to calculate project duration and probability of completion. Let's get into the class. Here's what you'll take away today. Understand what PERT is and how it differs from deterministic method, which is your CPM. Learn how to calculate project duration using PERT model. Explore how to estimate the probability of meeting a project deadline. By the end of this training, you'll not only know the formulas, but you also know when and why to use PERT technique. What you're looking at now is the course schedule overview. So far we have covered the project planning and scoping in week 1. We did project scheduling CPM in week 2, and in week 3 we learned about the overlapping network diagram. This week we'll cover the one of another project scheduling technique, which is the PERT technique. Okay, let's start with an overview of PERT technique. PERT stands for Program Evaluation and Review Technique, and it's one of the most important tools in project management for dealing with uncertainty in schedule. It's a statistical tool used in project management to analyze and represent the tasks needed to complete a project. It was developed in the late 1950s. I think it's from the US Navy when they were exploring a highly complex and uncertain projects where traditional scheduling methods were not enough to calculate the duration of activities. So PERT and critical path method were introduced in the same decade, while CPM is deterministic, which assumes a single or fixed duration for each activity, and it assumes we know the exact duration of every activity. Whereas in PERT, it takes a probabilistic approach, which means assumes that activity durations are uncertain. We don't know what the duration could be. So this is because in real projects like research and development or any innovative projects, we don't always know the exact time or duration of task, how it's going to take place. So the PERT technique recognizes that activity durations vary. So instead of assuming a single estimate like the CPM, we use a range of estimate to calculate an unexpected time. Unlike CPM, which uses single estimate for activity duration, PERT uses three estimates. So it's called the optimistic, most likely, and pessimistic, which is all based on best case scenario, your normal condition, and the worst case scenario. So this gives us a range and allows us to capture uncertainty in schedule. By combining these three technique or three estimates, that's what it's called, 3-point estimate. PERT calculates the expected duration for each activity and then estimates the overall project duration. This allows project managers to answer questions like what's the probability we'll finish by a certain deadline. That's the most important thing about the PERT model. Okay, before going into PERT, let's see what the advantage and disadvantage of PERT technique. The advantages are it helps maximize resource usage. It makes planning manageable even when historical data is limited or unavailable. It enables managers to access the likelihood of meeting deadlines. And some of the disadvantages could be harder to interpret for complex projects. So many managers will still use Gantt chart along the side, and PERT can be tedious to update, and subjective estimates can introduce bias. So while PERT is powerful, it is not a silver bullet to address your complex problem. So it works best in projects where uncertainty is high and you need a probabilistic schedule. Okay, why do we care about probability here? So, well, project managers often need to answer the questions like what's the likelihood we'll finish this project by this date? PERT gives us that answer by calculating an expected duration and using the probability distribution to determine completion of likelihood. So this is critical for managing stakeholders' expectation and planning contingencies. PERT treats each activity's duration as uncertain, so rather than fixed like the CPM duration technique. So when you don't know what the duration of an activity could be, instead of using one number for duration, PERT technique helps you identify duration using 3-point estimate or three estimate concept, which as I explained in the previous slide, it's about optimistic, most likely, pessimistic approach of an event, of an activity. In the following slides, we'll go through what those are in details. And using this 3-point estimate, PERT models each activity duration as a random variable, which they call traditionally a beta shape. So if you look at the center one, that's your beta distribution, how each activities could be, you need to work on different points of that estimate. Using the 3-point estimate, we compute an expected time and a standard deviation for each activity. Then we combine the uncertain activities along the critical path to get the project's expected duration and variability. Finally, we use the normal distribution, the standard normal distribution, your third picture, to answer what's the chance that we finish by this certain date or expected time. Since activity durations are uncertain because we don't know the probability of an activity, PERT technique relies on probability distribution, which assumes they follow a beta probability distribution, which is called a distribution that can take different shapes depending on the estimates. So the center diagram shows what are the different forms of activities or shapes that can take depending on the estimate that we come up with. A beta distribution for activity time and a normal distribution for project duration. So it's very data driven. So to simplify the calculation, we then approximate using the normal distribution for the overall project duration. That's the main thing about the PERT. So the both beta and normal distributions play key roles in how PERT models uncertainty of activity. So this is the major concept, the probability concept used in PERT. So the beta distribution is a continuous probability distribution defined on a finite interval. Usually they have 0 and 1. It can take different shapes, symmetric, skewed left, skewed right. You need different the bar chart going everywhere, or not the bar chart, the line charts going everywhere. Make it flexible for modeling uncertainty durations that have a minimum and maximum bound. So why PERT uses this beta? Activities times cannot be negative, right? It cannot have a negative time, and usually have minimum, which is your optimistic point, and maximum value, which is your pessimistic point. So beta distribution can represent this bounded nature well. So it can take into the optimistic point and the pessimistic point and bound well about this. PERT assumes the activity duration follows this beta type distribution because it reflects uncertainty between optimistic and pessimistic time. It accommodates skewness, which is what we call activities often take longer than expected, so the distribution may be skewed right. So let's now see about the third graph, which is your normal distribution. So the normal distribution, which is your bell curve, is a symmetric distribution defined by two element, which is your mean. Mean is the average of a set of numbers calculated by summing all the values and dividing by the number of values, which gives you your expected value. Whereas the second point is the standard deviation. The standard deviation is a statistics that measures the spread or dispersed of data points around the mean. So if you look at the diagram, the black line is your mean. That's your center point, which is your mean. And if you look at sigma 0, sigma 2, sigma 1, sigma 3, those are all the how much you're looking at the measure that spread or disperse of that data point around the mean. That's how you do the spread of distribution. That's how you calculate your standard deviation. So a low standard deviation indicates that data points are clustered closely around mean, while a high standard deviation indicates they are more spread out. That's pretty much it. So standard deviation is used in PERT because it is the most common and effective statistical measure for representing uncertainty or variability in project duration. So in PERT, each activity has a range of possible times, which we know, the 3 point, and this range indicates uncertainty. But just knowing the range isn't enough. So you need to quantify that measure of how uncertainty the estimate is. Standard deviation measures how spread of out of values are around the mean. A bigger standard deviation is greater uncertainty. And also in PERT, an activity's duration is equally likely across the range, and most likely estimate carries more weight. Standard deviation reflects how far pessimistic and optimistic times are from the mean. If pessimistic and optimistic estimate are very far apart, standard deviation will be large, project risk is high. That's how you do. You use standard deviation to calculate the project, whether it's high risk or low. Now let's look on to the 3 point estimate. So the 3 point estimate is the heart of PERT. So for each activity, we estimate the optimistic time, which is we refer here as A, the shortest time the activity can be completed. That's an assumption. Assuming everything goes perfectly, roughly a 1% chance. Okay, that's how you give your optimistic time. The second one, the second estimate is most likely, the best estimate under normal condition this activity can be completed. And you have the third point, which is your pessimistic, the longest time that the activity might take, assuming everything goes wrong. That's your pessimistic estimate. Also about a 1% chance. By using these three values, we capture the range of uncertainty for each task or activity. And let's see how it's applied. So these definition define the shapes of beta distribution for that activity. So the 3 point timing, the optimistic, most likely, and pessimistic time, define the shape of beta distribution for that activity. Instead of complex beta mathematics we want to use, let's PERT simplify by using expected time, which is your TE, your small te equals your optimistic plus 4 times your most likely, which is your M, and your pessimistic divided by 6 as an expected value, which is your obviously your mean. So you're taking average of your pessimistic, 4 times of your most likely, and pessimistic, and you calculate the expected value. And how do we calculate the standard deviation? So the standard deviation is calculated by your pessimistic value minus your optimistic value divided by total number of time or value that you have taken, which is 6. This captures the uncertainty. The bigger the range, the bigger the standard deviation. So let's think about an example using we'll use a prototype example. So if you have want to calculate how many weeks you want to have this activity to be done. So your estimated time could be you're making one optimistic value as 2 weeks plus your 4 times of your most likely time, which is your 4, and plus your very pessimistic, which would take 8 weeks. And you all calculate, you add that, you sum all those numbers, divide by 6, which gives you 4.3 weeks. And in the standard deviation, what you do, you take the pessimistic value, which is 8, minus your optimistic value, 2 weeks, divide by 6, which gives you 1 week. That's how you do the calculation for using the 3 point estimate. Okay, let's now see how to calculate the expected project duration using a 7-step process. Now to calculate the expected time, which is TE for an activity, it's a usual formula as just told in the previous slide. The expected time TE, small t e, equals the optimistic time, which is A, 4 times of the most likely, and then the pessimistic B divided by the total, so which is 6. So we give more weightage to the most likely estimate because it is generally the most realistic approach. And for standard deviation, which we call it sigma, equals your pessimistic minus your optimistic value divided by 6. So what standard deviation captures is the uncertainty. The bigger the range, the bigger the standard deviation is. So why PERT uses normal distribution? So the project completion time is the sum of many activities duration. As we all know, it is, you calculate all the durations of the activities, and that will give you the sum. But again, we need to calculate the critical path, especially those on the critical path, right? So the critical path activities total durations will give you the project completion time. So when you sum multiple random variables, the sum tends towards a normal distribution approach. So as like seen in the previous slide where we saw beta distribution and normal distribution. So this one tends to towards a normal distribution even if individual activities are not normal. So the total project duration is approximate as normal with sum of all expected time calculated for the critical activities. So now you sum all the expected time, which is t small e of critical activities to get the expected project duration. So how do we calculate the mean for the total project? It is the capital TE, which equals summation of all your small TE, which is your small expected time for all the activities, or at least the critical path activities. This allows us to compute probabilities using a formula, we call it Z0. I'll explain more about Z0 in the next slide, but it's basically your project standard deviation minus your project duration divided by your S, your capital S, which is your sum of all the standard deviation of that activities. That's how you calculate your Z0. I'll explain why we use Z0 in the next slide. Yes. And you generally use the normal distribution table to find the probability. That's the activity that we'll be looking at. I'll provide you with the probability table and for a normal distribution. Okay, so the step 4 is what we calculate the S square of activities for all the critical activity, right? So S square, why do we do it? So as we all know, mean is an average and it tells us where the data is. So this is only half the information we have. So when you calculate the expected time, which is the mean, it will only give you half of the information. We need to know how spread out the values are. We need to look at all the, if you look at the bell curve of normal distribution, you need to know the spread out of values are. So that's where the standard deviation comes. Calculating standard deviation is by square rooting the variance, which is the average square distance from the mean. So variance and standard deviation are fundamental concept in statistics used to measure spread or disperse of a set of data point. So if you look at the bell chart, your standard deviation will be at the x-axis, and then the variance is about the spread or the disperse of data set points. So variance quantifies how much the data points deviate from the mean. So you have mean at the center. So your variance will tell how much the data points deviate from the mean. While the standard deviation provides a measure of the distribution of data points around the mean. So it gives you the measure of the distribution of data points, which we can see in the bell curve. It's about sigma 1, sigma 2, sigma 3, and so on. So the variance is calculated by subtracting mean from each value, square it, and then take average of those numbers. That's how you do the S square activity. So why have two different numbers to measure the spread for normal distribution? Variance gives an intuitive way to measure spread. It gives you an intuitive, like this is how it could be in a measure spread. Then by squaring the measure from the mean, we ensure that all values are positive, which makes sense when talking about distance. So another thing you need to take into account is the unit. So if you think about unit like centimeter or millimeter or inches, how you are calculating your data, that is more important. So when you do the variance, it becomes, so for example, if your mean is you're calculating the height of a person or height of a group of people in an organization or something, so your height, you look at whether it's inches or centimeter. So if you do the centimeter, then you do the variance, it becomes centimeter square. So unless you do and it becomes very hard when you compare with centimeter to centimeter square. So right. So now you need to square root that variance and becomes centimeter. So now you have mean and the standard deviation so that you can compare with the mean of that of a particular activity across a spread of different data. So when you do the square root of that variance, easily standard deviation can be calculated. Now, to calculate the total SD, the capital S, is your step 5. So that's how you do your summation of all your like all activities standard deviation, and then you square root it. So now compute the project standard deviation by summing the squares of critical activities, which is your sigma values, and taking the square root. So now you have the mean and standard deviation for the whole project. That's how you do the calculation. Now, so what before we are coming into Z0 Z number calculation, PERT assumes the total duration or the total project duration follows an approximate normal distribution, which come from a theorem called central limit theorem, which explains that given a significantly large sample size, the distribution of sample means will be approximately normal, regardless of the shape of population distribution. This is a kind of a powerful theorem, allows statisticians to make inference about a population mean using sample data, and even when the population distribution is kind of unknown. So when calculating the sum of standard deviation and mean, the variable z represent a score, which is a standardized measure indicating how many standard deviations or a particular data point is away from the mean. So you need to calculate how many standard deviation a particular data point is away from the center point, the center mean. It is a statistical measure that describes the position of a raw score in terms of its distance from the mean. So you calculate this whether it's sigma 1 or sigma 2, sigma 3, and that's how you measure standard deviation units. It tells you how many standard deviations a particular value is away from the mean. So when we have our bell curve, the mean goes in the middle. As we all know, the mean is in the middle. The z-score is going to tell us where in relation to that mean a certain value is. Any value that would be to the right side of the mean is going to have a positive score. A positive z-score indicates that the value lies above the mean. Any value on the left side is obviously your negative z-score, which indicates the value lies below the mean. And z-score tells us the location where on the bell curve the value would fall. That's pretty much it is. And why do we know it? To calculate the chances of finishing by a target date, we use z-score formula, which is nothing but your capital T, your expected time of the standard deviation minus your expected time, the total expected time of the project, divided by the big S, which is your standard deviation of the project. So where, as you know, TS equals your target's schedule completion date, your TE is your expected project duration, capital S is your standard deviation of the project. Without S, you cannot convert your uncertainty into a probability. Now the Z score tells us whether it's positive score or negative score. If it's a positive score, the data point is above the mean, and the data point is below the mean for negative score. And there is also Z0, which means the data point is close to mean. And now you need to look at the magnitude of z-score. A larger absolute value of z-score indicates data point is further from the mean, meaning it is more unusual or extreme. Now, we need to know how z-score is calculated. Once z-score is calculated using, now you can use the normal distribution table to find the probability, which is your next slide. So look at the example here. So now the z-score of a particular project, it comes as 1.2. For example, we'll take it as one example. And probability of completing the project. Now you need to find out what is the probability of completing the project using the probability table. Now you look at the value of z. So z value is 1.24. Now you go across z and see whether 1.24 is there. So it's coming up down and you see 1.2, and then on your column you look at 4. So z is 0, 1, 2, 3, 4. This becomes 4, and if you look at the number, it becomes 0.8925. which approximately is 8.8925 into 100. You put you get your percentage. Now it shows this project, this of a Z score of 1.24 gives you a probability of completing this project by the scheduled duration is 89.25%. This is how your Z value for the Z score calculation helps you identify the probability, and then you can determine the project completion duration of that particular project. What percentage of this project or the duration can this project be achieved? That's how the normal distribution table will help us, and that correspond to the probability of completing on time. And if you have any question, as you all know, please do email me or Jin, and we should be able to help you in understanding this concept. This is quite important. And thank you so much for your time. And if you need any help, please do email us. Otherwise, have a wonderful day, guys. Thank you.